Okay, so imagine we want to build a cylindrical tank. And imagine this tank is made out of metal. And imagine we want the tank to be able to contain a certain amount of liquid. And so we want the tank to contain, or at least be able to contain up to 16 pi meters cubed of a given liquid. So naturally, when we build this tank with this prescribed volume capacity, we're going to try and build the tank in the cheapest possible way. So the question is, how do we choose the measurements of the tank so as to lead to the cheapest possible construction? Well, a cylindrical tank has naturally two measurements. It has a radius and of course the height of the tank. So how do we choose the radius and the height just right so that the tank can contain up to 16 pi meters cubed of a given liquid and simultaneously is as cheap as possible? So we ask, well, what function measures the cost of building this tank? Well, the ultimate cost will be how much material, how much metal is used to construct this tank. And if you think about this, the amount of metal used is calculated by the surface area of the tank, right? We have to construct the top, the bottom circles of our tank, and then the full body of the tank. So that corresponds to the surface area. So our goal will be to try and minimize the surface area with the given restriction. Now let me rewrite the volume in terms of R and H. So we know that the volume of a regular solid like this will be the area of the base times the height. The base, just like the top, is a circle, so the area is pi r squared times the height h. And of course we have a restriction. Pi r squared h must be equal to, and here I will drop the units, 16 pi. Now, how do we find the surface area of a cylindrical tank with a top and a bottom? Well, you can break down the tank into three core pieces, right? The bottom and the top. Both are circles with the same radius. So let me imagine you pick the top and the bottom off of this tank. So you get say the bottom, circle of radius r. You get the top, exact same circle of radius r. And then you're left with, after you remove the top and the bottom of this tank, you're left with the body of the tank. Now imagine this like a little bit of the cardboard of a roll of toilet paper. If you cut through one side of the body and you flatten this out, what you have is a rectangle. And the area of a rectangle, of course, is easy to find. Base times the height. Well, the height of the rectangle will be the height of our tank. And if you look back, if you think of wrapping this back to a body of a cylinder, well, the length of your rectangle is the circumference of a circle of radius r. That is, of course, 2 pi r. And now we can find the surface area of our cylindrical tank quite easily, right? The surface area is the area of the two circles, so pi r squared plus pi r squared, therefore 2 pi r squared, plus of course the area of the body, which is 2 pi r times h. So now we have our objective function, but the problem is that we have a function of two variables, r and h, so we have to find a way to reduce the objective function as a function of not two, but of one variable, and this can be attained, of course, with our restriction. If we go back, pi r squared h must equal 16 pi, so we have two options here. Either we isolate h in terms of r, or we isolate r in terms of h. it's better to isolate h in terms of r, because if you isolate r in terms of h, this will lead to, in solving for r, to a square root. So it will make things a little bit more complicated. So from the restriction, let's isolate h in terms of r. So let me rewrite the restriction here. So we have that pi r squared h equals 16 pi. So you want to solve for h divided by pi r squared. So h is 16 pi over pi r squared. We can of course cancel the two pi's, and we're left with h being quite simply 16 over r squared. And now we can make the substitution in our objective function. And h, again, is, and let me write h here, 16 over r squared. And we can simplify this a little bit, right? The first step is that both terms that we're adding have a common factors of 2 pi, so we can factor it out. So in the first case, we're left with r squared. In the second, we're left with, well, r 16 over r squared. If we cancel one of the r's, we're left with 16 over r. And we know that to minimize this function, again, minimizing the surface area leads to minimizing how much metal is used, therefore minimizing the cost of this tank. We will have to find the derivative of this function. And we can, of course, rewrite the quotient here as a single power of r, and avoiding the quotient will lead to a simpler differentiation. So we have 2 pi r squared plus 16 r to the negative 1. And now we have our objective function as a function of one variable. So what is our objective? To minimize this function of r. So we want to minimize this function. So a is a function of r now. So 2 pi r squared plus 16 r to the negative 1. And do we have a range for r? Well, r must be clearly positive, as it is the radius of a circle. And if you ask, is there an upper bound for how large r can be? Well, look at the restriction, right? Pi r squared h must equal 16 pi. So no matter how large of a radius you take, you can always take a very small height for the tank that will offset how large r squared is, so that the product will balance to 16 over pi. And you can also see it from the isolation, from the restriction. No matter how large the radius is, take h to be 16 over r squared. This would be a very small number, but with this choice of h in terms of r, the volume will always be 16 pi. So there is no upper bound for how large r can be. So since we now have a problem of minimizing a function of one variable, but we do not have a closed and bounded interval for the independent variable, we know we will have to fall back on the second derivative to classify our critical points. So right away, we will differentiate the area function twice, finding the first derivative and the second derivative. So a prime, is equal to 2 pi is a constant multiple, so it stays there. Derivative of r squared power rule to r. 16 is a constant multiple, stays there. R to the negative 1 power rule will get negative r to the negative 2. So we'll get negative 16 r to the negative 2. So here's our first derivative. Second derivative, again 2 pi is a constant multiple. Derivative of 2r is 2. Negative 16 stays there as a constant multiple. Power rule again. Negative 2 times negative 16 is positive 32. Times r to the negative 3. So now we have our first and our second derivative. And right away, if we look at the second derivative, we should notice something interesting, right? R is the radius, so it's positive. So the second derivative is 2 pi times positive number plus 32 times a power of a positive number. So everything here is positive for any choice of r. So the second derivative is always positive regardless of the value of r, which means if the second derivative is always positive, the function a of r, the area function of our tank, is always concave up. Of course, if r is positive, and this bodes well for our objective, which was to minimize this function. If it's always concave up, hopefully it will look a little bit like a parabola, and it will have a unique minimum. Well, the minimum we know should be achieved at a critical point, so where the derivative is equal to 0. So let's solve for the critical point. So Cp. So the derivative is equal to 0 if and only if, well, if 2 pi, which is a positive number, times this is equal to 0, then this has to be equal to 0. So 2r minus 16r to the negative 2 must be equal to 0. And now let's attempt to solve for r. The first thing is we have a common factor of 2, so we can divide across by 2, which will give us r minus 8, r to the negative 2 is equal to 0. Send this over here and rewrite r to the negative 2 as a 1 over r squared, which gives us r equals 8 over r squared. Multiply back up by r, so r cubed is equal to 8. Take the cube root on both sides, but 8 is a perfect cube. It is 2 cubed. So r equals 2. So now we have found the value of the radius that leads to a critical point of the area function. And again, we now have everything we need, right? Let's produce a very rough sketch of the area function, which again measures how much material is being used in constructing our tank. So the graph of A, the area function, versus r, the radius of our tank. And again, since r is the radius of our tank, r is positive. So we're only considering the graph of the area function for positive values of r. So r equals 2 is a critical point. And you could find the exact value of the area by plugging r being 2 in here. But then multiple of 2 pi doesn't really matter. This would be a positive number. Say it's here. And at this point, the derivative of the function is 0. This is a critical point, so at this point the curve is flat. And because of the second derivative, we know the graph of the area function is always concave up. So there's only one way, and notice also that this is the only critical point of our function a for the positive real line. So if you have a point where the derivative is 0, the curve there is flat, and because it is always concave up, it can only look like this. Essentially, more or less, a bit of a parabola. So this proves that, of course, this value of r leads to the absolute minimum of the area function. So this is the right answer. But of course, we wanted to provide a full set of measurements, not only the radius of the tank, but also the height. But recall that the height was 16 over r squared. So the height is 16 over r squared. But since r is 2, 2 squared is 4. So we get 16, 16 over 4, which of course is simply 4. So the radius of our tank must be 2, and the height of our tank must be 4. And now we can go back to including in our conclusion the proper units. The volume was in meters cubed, so the measurements in R and H are also in meters. So to have a tank that uses the least amount of metal possible and can contain up to 16 pi cube meters of liquid or solid. The radius, as we have just found, must be 2 meters, and the height of the tank must be 4 meters. And that is the optimal solution. Minimizing again the surface area of the tank, therefore minimizing how much metal is used, therefore minimizing the cost of building this tank. And again, we prove that these measurements are yielding the optimal solution using our first derivative to find the critical point, and the second derivative to prove that the critical point we found was indeed an absolute minimum. And that's it.